In this video, we will be using the integrated rate law to perform some calculations. In this example, we're going to use first-order reactions. A first-order reaction is a reaction where the rate depends only on the concentration of one of the reactants raised to the first power. So, the very generic rate law, rate equals the rate constant times the concentration of A. And then we take a look at our rate expression. Rate equals the disappearance of the reactant over time. If we combine these two, we get this equation. And if we apply calculus, it's possible to derive the integrated rate law for a first-order reaction. This is very useful. Now we can determine what the concentration of our reactant is at some time within a reaction, as long as we know the rate constant, the initial concentration, and how much time has passed. And of course, we don't necessarily have to be looking for the concentration at some time. As long as we know three of these variables, we can determine the fourth. So what do these mean? Well, don't forget, this is the natural logarithm, not the log base 10. A sub 0, well, that's just the concentration at time 0. Concentration of A sub t, that's the concentration at some time t. And of course, we know the rate constant. And time, well, time has to match the rate constant. Minutes, seconds, hours, days, years, whatever. Now, it might be interesting to note that there's another version of this first-order integrated rate law. We can rewrite it using the law of logarithms in linear form, and this becomes very useful in graphing. We can actually determine what the rate constant is based on graphing natural log of concentration versus time. So how do we use this? Well, for example, let's take the decomposition of hydrogen peroxide. This is first order. We know what the rate constant is at 20 degrees Celsius, and we've been told 20 degrees Celsius because we must keep the temperature constant. And we also know what our starting concentration of hydrogen peroxide is. We want to know what is the concentration after 3 hours, and how long will it take for the concentration to drop from 0.75 molar to 0.1 molar. Well, let's gather together all of our information and the integrated rate law. We want to solve for, initially, concentration at time of 3 hours. Now be careful, our rate constant is in per seconds. We need to convert our time into seconds. So now that we've converted our time to the proper units, basically all we have to do is plug this in. Now what do? Now we have to get rid of that natural log. To get rid of the natural logarithm, we just take E, Euler's number, actually pronounced Euler, and raise it to the natural log of our ratio. But we have to do that on both sides. Once we've done that, well, E raised to the natural log of x is just x. So we've essentially gotten rid of the natural log on one side. And of course, we have to take the E raised to the negative 0.1944 to get our value on the other. Now it's just a matter of solving for concentration of A after 3 hours, or in this case, concentration of hydrogen peroxide after 3 hours. Now this makes sense, that over time the concentration of the reactant is going to go down, and it did drop from 0.75 to 0.618. Now we want to calculate how long it's going to take in order for the concentration to drop to 0.10 molar. Same starting concentration, we know our rate constant, now we just need to solve for time. This one's easy, there's no anti-logs or Euler's number. It's just a matter of plugging everything in, being very careful to note that negative sign in front of the rate constant, and solving for time. In this case, we get a very large number. It might be better to write this in hours. Here's another example. Calculate the rate constant of the first order decay of carbon-14 if 75% of the initial sample is present after 2,378 years. So radioactive decay, that is a first order reaction. So we're going to use our integrated rate law for first order. At time 2,378 years, we have 75% left. Now, how did we write that? Well, we just gave a percentage, but we can treat this as if it's an actual quantity, because how much do we have in the beginning? We have 100%. How much is left? 75%. So it doesn't matter that we don't have actual compound, actual concentration. We just assume that at the very beginning we started out with 100% of the material. So now we solve for K, and that gives us the rate constant for the first order decay of carbon-14. Half-life is another interesting concept. Half-life is the time it takes for half of the original material to be consumed, or decompose, or disappear. So how do we find half-life? Well, actually it's pretty easy to derive this equation. We take our first order reaction, or our first order integrated rate law. We rearrange and solve for time. At time t, the concentration is going to be half that of the original concentration. So we just substitute this in and solve for t again. And this is a very straightforward calculation. Half-life is just natural log of 2 divided by whatever the rate constant is. So let's calculate the half-life of carbon-14 if we know its rate constant. So the half-life of carbon-14 is 5,728 years. What can we do with this? Well, how many half-lives have passed after, say, 34,368 years? Well, this is just a ratio of how many years have passed over the half-life. So in this case, after this many years, 6 half-lives have gone by. Alright, well, what percentage of the sample of carbon-14 is left after 6 half-lives? Well, percentage of the sample left, we're assuming we started with 100%. Easiest way to do this, we just take our 100% divided by 2 raised to however many half-lives have passed. So in this case, after 6 half-lives, only 1.56% of the carbon-14 remains. We can prove this little shortcut. Let's take the linear form of our integrated rate law. Let's plug in our rate constant, how many years have gone by, and our starting material, or starting quantity, 100%. And according to this, we take the natural log of both sides, concentration after 6 half-lives, 1.56%.